Hello, everybody. Welcome back. In this lesson, we will go over more examples for the product rule and then another related topic, which is about higher order derivatives. So first of all, since we are already familiar with the product rule and we already worked with some examples for the product rule, so why don't we just start right away with examples? First of all, recall the formula. The formulation is none other than, now here, other than using the notation d, I would use d by dx, which means this is not a fraction. First of all, try to understand. It is a special notation to indicate the process of differentiation, emphasizing the outline, the corresponding variable. So this particular variable, now we are trying to differentiate this function with respect to variable x. So if it distracts you by any chance, simply think about it like this means differentiate. That is the meaning of this phrase in mathematical terms. Differentiate. So differentiate what? Differentiate the function right in front. So you're trying to take the derivative of the function sitting right in front. And when you take the derivative, we know the composition. We first grab the first function, we take the derivative, combine it with the second function, the original version, together with the multiplication, and then you put a plus sign, and then you leave the original first function and the derivative of the second. So it is simply called like f prime g plus f g prime. It's that simple. In that way, you can just recall it simply like a portable version of this result. Now, let's play with some examples. You do not need to recall the formula explicitly to work with these examples. Things that you can do is to just follow the recipe. That's all. You have a first function here, and you have this. You have two functions. So the first and the second. By any chance, if you write them in the reverse order, because multiplication is commutative, so you can just switch the positions. That's not going to change anything in this process because this process does not require the order. All what matters is to grab whatever the first function right in front of you, take the derivative. And we know the derivative of x cubed is 3x squared. And then combine it with the original second function, which is just sine x. Look at this. I have the multiplication in between. And then plus. Then it's going to be original first function combined with the derivative of the second. The derivative of the second function, now, if you do not recall it, that's exactly when you need to have your formula sheet, or in other words, the summary sheet that we already prepared. So have it handy. And the derivative of sine is none other than just cosine x. And that's our answer. We will not simplify it any further unless it's required by an application. Let's proceed to another example. Here we have the derivative. We need to take the derivative of ex times tangent x. So when there is no sign in between, that simply means you have the multiplication in between. So sometimes it can appear with this dot, sometimes it can appear without the dot. So if it appears without the dot, that simply means you need to assume that's the multiplication. On the other hand, like by any chance, if you have an addition, subtraction, that sign should be there explicitly. Now, let's play with this example. The first function, ex, the derivative of ex, none other than ex itself. And then original second function. Now, when you write this, be careful. The derivative of the original function is essentially not changing much. It is exactly the same thing when it comes to the exponential, the natural exponential. However, you need to understand that you place the derivative here because when you make a slight difference to this particular term, you will see it will completely appear, it will appear in a complete different form. So Try to understand, I did not copy the original function here. I just took the derivative of it, which happened to be the original itself. And then original first function. Now it's just the original. I am just copying this function and putting it right there. And then the derivative of the second, secant squared x. And that's my answer. I'm not going to simplify unless it's demanded by an application. So this should be fine. And then let's play with one more example. Here we need to take the derivative of a polynomial times a trigonometric function secant x. So when you take the derivative of this component, we know we use linearity properties because we have addition, subtractions, constant multiples, and everything. So use them in that level accordingly. First of all, I'm going to grab this function and I'm going to take the derivative. So 3x squared minus 5 times. Now, when I differentiate this, I'm going to end up getting 2 in front. So it's going to be 2x. Together with this negative 5, it's going to be negative 10x. And then plus 2, that will disappear because that's a singleton term, which is a constant, which happens to be a constant. So now at this point, this times secant x. Now be careful. If I write it in this way, it may or may not provide this precise idea. In fact, it could be ambiguous. The reason is, now here you have multiple terms when you differentiate this, then you need to have parentheses to gather them. If you do not have parentheses, now for instance, if you input this kind of an answer in a computational algebra on your computer, if you miss this parentheses and if you leave it like this, it will not recognize it correctly. So have parentheses, and then now the second component, original first function together with the derivative of the second. Here comes a step where I may need a little more space, so I will buy some space this times. The derivative of secant is secant x times tangent x. And that's where we are going to stop the computation. And again, I emphasize the importance of parentheses right here and right there. If you do not have parentheses, if you forget parentheses, then your answer may be subject to some revisions even in computational algebra. So pay attention. And then let's look at one more example. Now, what is the specialty of this example? Take a moment, pause the video and try it yourself. Now, this is valid always, like even if there's a problem that I'm not gonna ask you to do it before me, always. If you're curious about what you're learning and if you would love to earn confidence, that's exactly one of the key components that we need to earn, right? So for that case, I always recommend whenever you see a problem, when I'm going to start a problem, the first thing that you need to do is to pause. Don't look at the solution. Just try to do it yourself. And that's how you can grow your mindset towards problem solving. Challenge yourself first. And if it's not going to work, if you need some more help, then the help is on the way because we're going to have the explanation. Take a moment and try and see whether you can do this problem. All right, I hope you gave it a try. Now let me show you something related to this problem. Now in this case, we can see it is a multiplication of functions, but if you look at very carefully, you can see it is not only two multiplications. In fact, you have three different components in it. When you have three different components, how can you work with it? Now, in our product rule, at least in the version that we have as a rule, we have only two functions. So we know how to deal with two functions, but we do not know how to deal with three functions. Is it going to matter? Now, this is exactly where the sequential thinking in mathematics would be helpful, right? So when you learn something simple, then the next step is to extend it to a slightly more complicated scenario and see if that tool would work. If not, that's exactly when you need to think about more sophisticated tools. In this case, our tool would work perfectly, because this is what I'm going to do. First of all, let me gather these two functions and leave this one function as the separate one. So if you look at it like this function is just like f and this one like g, now you have the perfect setup to begin with at least, right? I will show you a couple of steps in this process. The first step, mm, I'm going to take the derivative of the first one. I'm going to take the derivative of this piece. Now, don't forget, now think about it. When we are up to taking the derivative, when you're about to take the derivative of the first function, look at the structure of that component. It has two pieces. It's a multiplication already. Now you need to think about the rule that you need to use. So what is the rule? To use the derivative, to take the derivative of a product of two functions, you need to use the product rule. So since it could get complicated and it could get a little messy when you work with complicated enough functions, let me show you an easy way of doing this. Why don't you just indicate that step and do it in the next step? Look at this. I need to take the derivative of this. Well, it has more complicated pieces, therefore I'm not going to compute that right away. So let me say I need to take the derivative and I will keep it for the next step. And then original second function, which is going to be cosine x. And then plus, then the original first function, which happened to be the product of those two pieces. Now, since we are not taking the derivative of that, we do not need to worry. And then we take the derivative of the second component, that will be negative sine x. Recall the derivative if you do not recall it. Now, the way to use your formula sheet, try to recall it first of all by your muscle memory, because you took the derivative of sine, you know it's going to be cosine. If you have that memory, at least, right, try to access it and try to write the answer in that way. If that does not work, only you can go ahead and check the formula sheet. So in that way, you can familiarize yourself with that one single page of formulas. Now, let's return to this problem. Look at this. This is not the final answer, because now I ask you to compute this derivative and you gave me this line where there's an unprocessed derivative is yet appeared right here. It is not processed because it's still having d by dx in front. In other words, it says differentiate something. I ask you to differentiate something and you're giving me an answer. Okay, get your answer with after differentiating this thing. But that is not a complete answer, right? So we need to take the derivative. Let's take it now. Since we know by experience there will be two terms. You don't need to close parentheses, but there will be two terms. So for that case, start parentheses right away. Now take the derivative of the first component, which is going to be 2x times ex, which happens to be the original second function, plus then original first times the derivative of the second, which happens to be just ex itself. This is the derivative. And then right after that, now this happens to be, this is none other than just the derivative that you expanded after taking this. And then times cosine x plus, here this is a multiplication, so we do not need to have parentheses around it. And then don't forget, here you have plus, right? Here you have plus, but there is a multiplication with this negative sign. Therefore, it will change the sign. So I can just do it right away. Since, okay, so it is with the simplification. you can convert the answer to this form, and that will be accepted as the final answer. However, at this point now, by any chance, if you include this kind of an answer in, let's say, for instance, in Mathematize, when you work with your numeric inputs, by any chance, when you input the answer in this way, it should recognize the answer correctly, as far as you didn't do something like this. Let me show you a surprise. By any chance, if you put this without parentheses, now there's an ambiguity. Should we just subtract? Should we have it multiplied? So have parentheses to make sure to emphasize that you multiply that term instead of adding it or subtracting. So as far as your output is mathematically readable, mathematically accurate, it need not to be the most simplified form when you input the answer. So let's look at one more example. Now in this scenario, we do have, like, let's say a product of 4 different functions, and they are intrinsically different. In other words, you cannot have simple ways to combine them, right? So how do you play with this? Now, I mentioned earlier, we can just gather these functions and differentiate. Now, there are multiple ways of doing this. Now, earlier I said, like, let's gather the first 2 terms and leave the next one separately. But one may say, like, okay, should we do it like just like that? Should we just gather the first 3 terms as one combo and this one as a second piece? You can do that. And we know how to deal with the product of 3 functions already. Therefore, if you get the answer, it doesn't really matter which way you're going to separate or gather these terms, put them together, bundle them. Whichever the method you prefer, it's going to result the same answer, which is up to just a simplification. So simply, you can just bundle this one with that, and you can bundle this piece with that in that way. And if you take the derivative, it's going to be the same answer. So it's not going to harm in any possible way based on how you're going to bundle them. So since we know that fact, let me do it simply without making things much harder. I will just gather these things as they are already. The first 2 and the second 2. Now, let's take the derivative. This is my way of working with the problem, but feel free to have different combinations. If you'd like to gather 3 functions together instead of having two and two at a time, go for it and see how it's gonna result in the same answer. So first of all, we're gonna take the derivative of the first. We know it has 2 components, so I'm not gonna rush. I will just leave it for the next step. This times the original second function, so I will just write it like tan x times ln x plus. The next step is to leave the original first function, so ex x to the 7, and then I am going to take the derivative of the second component. Now let me just indicate it again just by the symbol d by dx tan x ln x. Now all you need to do is in the next step, like, to expand this by taking the derivatives, and then the recipe, the complete recipe is already available. You put everything in the positions. So the first one, the derivative of the first component ex together with the derivative of the second one, original of the second, so x to the 7. Don't forget the parentheses here because we will have 2 terms. And now original first function and the derivative of the second, which happens to be 7 x to the 6 times tan x ln x plus ex x to the 7. That's already there inbuilt right there. Now I'm going to take the derivative of this component by the product rule. So when you use the product rule, let me buy a little more space here. Take the derivative of the first component, which is going to be secant squared x times original second function ln x plus. Now original first with the derivative of the second. So tan x times 1 over x. 1 over x is exactly the derivative of ln of x. Now I had to squeeze this into like to a tight space because the answer looked lengthy. But look at this. The answer did not take long. It took only 2 steps. This can get considerably tedious when you have, like, let's say 20, the product of 20 functions, other than having 4 functions like this. But yet the process is exactly the same. You can gather them, you can bundle them, and you can consider 2 at a time, and you can proceed. So it doesn't really matter how many functions you have in the product. You can always use the product rule to compute the derivatives involving the products of functions. So let's proceed with that to see one more example here. Example number 6. We can consider this as the conclusion to the lecture. So let's try to first of all see uh, this by using the product rule, right? You have just the direct product rule. So why don't we just take the derivative as it is? I'm going to take the derivative. So when I take the derivative, now this is not a surprise, right? You have only 2 pieces and you know the derivative of cosine, you know the derivative of tangent. So what is the big deal behind this problem? There is none, right? So let's take the derivative of cosine, which happens to be negative sine x times original second function plus. Then you're going to get original first function, original first, together with the derivative of the second. And that's pretty much the answer. You can leave it like that. However, let me give you just a quick remark related to this problem. By any chance, if you recall the simple fact of this trigonometric simplification, cosine x times tan x. Now, sometimes when these functions are coming from the same universe, which means they can interact with each other. Now, exponential and trigonometric, they're coming from different universes. They cannot interact. However, trigonometric with trigonometry, perhaps there could be a way to interact. That means, in other words, you can simplify cosine x times sine x divided by cosine x. You need to recall the simple trigonometric fact that tangent is none other than sine x over cosine x. Look at this. That is the basic knowledge that you're supposed to have. And I just even recall that simple fact because I told you right at the beginning of this derivative compartment. We do not assume anything from outside. All we need is just knowing the derivatives. That's all. So by knowing this simple fact, if you recall that, you can substantially simplify this problem because the cosine gets cancelled and you leave with the derivative of sine, which happens to be just cosine x. The answer is that simple. Now the question is, do you really have that answer here? Did you get it right there with the first problem? Now, the answer, yes, it is just up to a simplification. You need to simplify it a little bit so that you can see that fact. So now in this occasion, I do not need to show all the steps how it would work in that scenario, but I can let you know a couple of things. Cosine x and secant square, cosine and secant are mutually reciprocal to each other. So mutually algebraically inverses to each other. So cosine x times secant, one copy of secant x would simplify right away. So if you try to simplify this answer a little bit, I will give it a little bit of a expansion so that you can see the first one, and then the second piece. This is none other than cosine x times secant square. One copy of secant would cancel with cosine, leaving just secant x. And once you have secant here, now at this point, if you write everything in terms of sine and cosine, possibly you can see some simplification. Sine x over cosine x and plus 1 over cosine x in the position of secant x. Now, what is secant x? If you recall the very basic definition of secant in trigonometry, that is none other than 1 over cosine x. Now, if you simplify this, you're going to get uh, the common denominator of cosine x, and you have 1. I will write this 1 in front, 1 minus sine x times negative sine x, that is negative sine squared x. If you recall this from trigonometry again, now the whole purpose is like this is the answer from calculus. You do not need to simplify it any further. If you infused it a little bit with trigonometric knowledge, you can get the answer easily. But we are trying to see that these two are the same. To do that, that's exactly when you need to load your trigonometric knowledge base a little bit for simplification. So 1 minus sine square is none other than cosine squared x, right? This component at the top is just cosine square, and at the bottom you have cosine x. That will simplify to cosine x. Now, if you do not recall the fact, 1 minus sine square, if you have difficult time in recalling this particular fact, how did we get this? That is what we call the Pythagorean identity. Let me just have it in a small box here separately. Sine square x plus cosine square x equals, this is called the Pythagorean identity, which happens to be just 1. So if you move sine square to the right side of that equation, you end up getting cosine square equals 1 minus sine square, and that is a replacement that I used here. Now, couple of things. Wait a minute, what is our answer? Now we talked about too many things here, right? We had method number 1 for the answer, and then we had method number 2, and we did somewhat work in this green section to connect these two, the red component and this answer, the orange answer and the red answer here, right? When it comes to your calculus answer, you can stop right here, right at this step. That is your answer. When it comes to calculus answer, you can stop right here if you just recall the fact that tangent is none other than sine over cosine. However, I wanted to show you these two answers are the same. Now, that is exactly what's happening. Now, we can compute derivatives just for taking derivatives, just compute them, even without knowing what these functions or where they're coming from. However, if you add a little bit of context to this picture, and if you come up with some properties behind the curtain, right? So when you come up with these a few properties, when you add a few properties, you can get some delightful results. So that is exactly what you're seeing here. You have two different methods, and yet they would result exactly the same. So with that, we will conclude this lesson, which was based on the product rule. And uh, once you're familiar with now these rules, now here, this is just a product rule. And we can learn these rules separately, and then ultimately we are going to mix them, and in that way you're going to see these computations again in a different layer of computations of derivatives. So that will be the conclusion of this lesson. We will meet on the next one.